Now, we finished up section 6 on Friday. Any questions there? We didn't, well, we started and finished up, I should say. Anybody have any questions? All right, so I'm just making sure I got everything going here. I want to. So questions over section 6, we talked about transformations, I believe. Yeah, transformations of those 12 basic functions. All right. Now, today, realistically, we're going to talk a little bit about some word problems. Just one thing to note, in the quick review of section 7, there's a bunch of formulas there. You don't necessarily have to have those memorized, but just a little review of some formulas that you should be familiar with. Okay, so this is going to be a lot of word problems in this section. Okay, and we can go over some things tomorrow as needed. But for the most part, it's going to be modeling with functions. That way we're going to be, let me just find this. All right, we'll be looking at a word problem, trying to figure out the relationship to use, and we'll have to solve it somehow. So we're going to look at about, I don't know, 3 or 4, maybe 5 different examples of some word problems. Okay. All right, first one. It says, and this is a common problem that we've, hopefully, maybe you haven't seen before, but it's a common thing, example of a problem that is used quite often. So square sides of X inches are cut out from each corner of an 8 by 15 inch piece of cardboard, and the sides are folded up to form an open top box. Right, so you can see in the diagram down here in the bottom, if we were to kind of cut out these little corners here, and we'd fold on the sides and fold up, we'd form a box like that. That makes sense? Okay. Now, it's our job to try to figure out what dimensions of this, what size square should be cut out of here so that we get the box with the largest volume. Okay, so we want to find the maximum volume. Okay, so the first thing we have to do is figure out, well, we're talking about finding the volume of a box. How do we find the volume of a box? Pretty easy. What do we do? Yeah, the volume of our box is going to be the length times width times height. Okay, now this is going to be that line in red there, that's going to be our length, isn't it? And I think our length is going to be 15 minus 2x. Now, how did I come up with that? Dylan, we got a math. No, I'm just reminding you, no big deal. It's like, what the heck? You look different. All right, 15 minus 2x. How did I get that? Yep.
Because 15 is what we're given. It's 8 by 15 and times 2x is the 2 boxes.
Yeah, 15, and then we're chopping off x on the top and the bottom, right? Everybody with me on that? Then, similarly, what would this dimension right here be? Using the same idea. This little piece right here. Whispered 8 minus 2x, that would be our width. Okay? Yeah, same idea. And what would our height of our box be? That would be right here. What do you think? Well, if I cut off x and then I fold it up, what's the height? What's the height? Yeah, it's just x, right? Because this dimension right here would be the same as this dimension right here, wouldn't it? Because we're going to fold that up. Okay. So that would tell us our volume is going to be 8 minus 2x, 15 minus 2x, and I'm multiplying here, times x. All right, that would be our volume function. And we built that using that diagram. Okay, we built that using that diagram. All right. Now, next part says find the domain of v as a function of x. Okay? Find the domain of v as a function of x. So, what would be reasonable values to plug in for x in our volume function? Okay, now think about this. This is a real world problem. So we'd have to think in the context of the problem, what numbers can we plug in there? Okay, looking at that function, what are some numbers that what's maybe the domain we could use? What's one thing you'd have to consider right away? What kind of numbers can't you have?
Negative.
Can't have negatives, that's right? What else? Less than the length. So you're saying, I'm hearing 0 to 15. Okay, it's going to be smaller than that. It's going to be 0 to something else. Okay, 0 to 8 still too big. Here's why. What if I put in 8 for x right here? My width would be what kind of number? A negative. 0 to 4. 0 to 4. Okay. If I put in something smaller than 4, I'm actually going to have a width, and that's going to work out to have a volume. Correct? So we just had to think. We said 0 to 15. Nope. 0 to 8. 0 to 4. Right? So that's going to look like so. Oops. What did I bump here? All right. There we go. So our domain is going to be from 0 to 4. Not including either one of those zeros or 4. I'm using interval notation. Okay? I'm using interval notation. So now we're up to part C. It says graph V as a function of x over the domain found in part B. Okay? Once you get out Desmos, and once you do that, you only want to look between 0 and 4, but you're going to look for where the volume function, which is going to be like our y value, hits the highest point. Okay, so we're looking for the peak, where it hits the high point between 0 and 4, right? We wouldn't look out anywhere between x equals 0 and x equals 4, because those would not be in our domain. See, it's up here somewhere, right? There we go. All right, so this is a maximization problem. All right, everybody able to find that? Question?
I don't know if I have the right number.
Well, I guess we'll find out. What did you get?
Like a point?
X equals what?
1.667.
Is that what you guys got? Okay. They got the same thing. That make you feel better?
Yeah.
Okay. So they're saying X is approximately 1.67. And what was your Y value, Peyton?
90.741.
All right. So this tells us to get the maximum volume, we should cut out squares that are about 1.67 by 1.67. What is this number telling us? If we do that, is that our volume? 90.7? Yeah, because that was our volume, right? Our Y value was our volume. Okay, our Y value was our volume. Okay. So we just used our the Desmos to find that value, find that P. Okay. So the maximum volume is 90.74, and that is when X is 1.67. Okay. Have you seen a problem like this before? Formula box? Maybe not. Okay, maybe not. All right. Questions? All right. Here's another one. Grain is leaking through a hole in a storage bin at a constant rate of 5 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone is always remains equal to the radius. If the cone is 1 foot tall now, how tall will it be in 1 hour? Okay. Right, so I think drawing a picture might help. It says that the grain is forming a cone-shaped pile on the ground below. Right, there's our pile of grain. Okay. It also said that the height and the radius are always the same, correct? Of our cone. Okay. It also says right now the height of the cone is 1 foot. And we want to know the height of the cone in what? 1 hour, which I'm going to rate as 60 minutes. Because this is given in cubic inches per minute. Okay. So how are we going to use what we're given here to kind of come up with an answer? Basically, the pile's going to be taller, right? We want to figure out how tall it will be in 1 hour. Okay. So what are some things we should try to use here? Or what's maybe a strategy we could use here? Or talk me through what do you think we should do? What formula might be important here? Well, cubic inches, what type of a measurement is that? Volume. So we might need to know the volume of a cone. Okay. Volume of a cone is 1/3 pi r squared h. Is that right? 1/3 pi r squared h. Now, a couple minutes ago, I said, let's change this to 60 minutes. Should I also change this over here? 1 foot. Why would I maybe want to change that? Or what would I want to change that to? Inches, because this is in cubic inches also. Okay, so I'm going to erase this. And I'm going to go back and change that to 12. And we could convert it later, but it's just going to be easier if we do it now. Okay, so can we find the volume of the pile right now? Do we know the radius? Same as the height. Do we know the height? Yes. So what's the volume right now? Find that for me. 1/3 pi r squared h. R and h are both 12. Okay, so it's the volume of a cone, so we're using this formula here. All right. Now I'm guessing you have a decimal. Could we figure out this number is in terms of just pi? What I mean is we don't need to multiply this out here, right? So basically, if the radius is 12, 12 times 12 is what? 144? And if the height is 12, that would be 12 times 12, 12 times 12. So what's 12 cubed divided by 3? Somebody find me that. 12 to the third divided by 3. 576. Is that right? Just did that in my head real quick. I have a headache. 576 pi. Okay. Now, what's going to happen? That's the volume of the pile right now. What's going to happen? It's going to get what? Bigger. How much bigger? What volume is going to be added to that in 60 minutes? Right there, right in front of you. What's the volume going to be in an hour? Or how much is it going to change in an hour? I'll read it to you here. Grain is leaking through a hole in a storage bin at a constant rate of 5 cubic inches per minute. If the cone is 1 foot tall now, how tall will it be in 1 hour? Well, how many increases of 5 cubic inches are we going to get? 60. So what's the increase in our volume? What is it? 300, yeah. 60 minutes, 5 cubic inches per minute, that's going to be 300 cubic inches. So our volume is now 576 pi plus 300, and that should still be 1/3 pi, can I say h cubed? If the radius and the height are the same, can I just say it's h cubed? Substitute them. All right, so then realistically, we just have to solve this equation, and that'll tell us how high the pile is now. Now, how would we solve that algebraically? It's not crazy difficult because there's not a lot of moving parts there. Remember, we're in pre-calculus here. What do we do to get h by itself? Okay, I'm going to take it times 3 and then divide by pi, same thing. So if we take 576 pi plus 300 times 3 and divide it by pi, would that be h cubed? And we could find that number on our calculator. And then how do we get rid of h cubed? Cube root, yep. See, so like I said, it wasn't too bad. It means it's a 3 by the way there. So that would be how high or how tall the pile is now. The cube root of that expression right there. Okay, so there wasn't a lot of crazy algebra with this one. It was more working with numbers, I think. Okay. But I think a picture helped. Knowing the volume formula for a cone helps. All right. They would have a number. What'd you get, Adam?
12.63.
12.63. Anybody else get the same number? Okay, so it really hasn't gone up much, right? It was 12 inches. Now it's not even 13 inches, right? And I think I have a slide here that gives us that answer there. You can see it is 12.63. Okay. So we used the model. The model we used there was the volume formula for a cone. Seemed to work really well. It seemed to work really well. Questions? All right. Now we're going to look at a couple questions from the book, just because we looked at a problem involving area. We looked at a problem involving volume. Excuse me, those aren't the only things we'll see. But so we're going to look at a couple more from the book. So open your books to page 149. And I've got a few we're going to look at here. First one is number 32. Okay, this is a mixture problem, and mixture problems are quite common. Okay. Right. It says a chemistry lab at the University of Hardwoods keeps 2 acid solutions on hand. One is 20% acid, the other is 35% acid. So basically, with those two, they could make any mixture that's somewhere between 20 and 35, right? They couldn't make anything more than 35. I suppose they could make one less than 20 because they could dilute it, right, with water. But with those solutions, they can make different mixtures here. Now, says, and this is an example where it's going to lead us to what's called a system of equations. How much 20% acid solution and how much 35% acid solution should be used to prepare 25 liters of a 26% acid solution? Okay, so we have 20%, 35%, and we want to end up with 26%. Now, would you agree if we wanted to make a 27.5% solution, would we mix equal amounts of each? If we were going to go 27.5% solution, we would mix equal amounts of each. So my thought is that I think we're going to use a little bit more of this one. Right? We're going to use a little bit more of the 20%. Just telling you there. All right. Now, here's our first equation I think we can come up with. If I allow X to be the amount of the 20% solution I need to use, and if I allow Y to be the amount of the 35% solution I use, those two amounts must add up to 25. We're going to end up with 25 liters, right? So the amount of the 20 plus the amount of the 35 has to add up to 25. Okay? There's no way we could do less or more than that. Right? That's our first equation. So once again, I'm kind of lining things up with where they are. Now, the next equation when we're dealing with mixture problems deals with our concentration or our percentages. All right? 20% of X is acid. 35% of Y is acid, and we're going to end up with what? 26% of 25 liters that is acid. Okay, this deals with the rates or the concentrations. Right, so what's meant by that first part is 0.2x. That means that 20% of that solution is acid, right? I don't know how much I'm going to use, so that's why I replaced it with X. Same thing with the other one, 35% of that other solution is acid, and this is our desired amount. Do you kind of see that equation in red embedded in the green one? X plus Y equals 25. It's kind of there, right? Okay. All right. Now, how do we solve something like that? How do you solve a system of equations? What are some options?
Substitution.
Substitution. What else? Elimination. We could graph also. Okay. I'm going to go with substitution. And if you really wanted to graph the check, you could. Because this top equation very easily can turn into this. Is that right? X equals 25 minus Y. And if I plug that in here, I'm going to get 0.2x plus 0.35y equals 0.26 times 25. So I've gone from two equations with two unknowns. Now I have one equation with one variable, and that's a linear equation, which we should be able to solve fairly easily. All right? It's a linear equation, okay? So take a few minutes and solve that for me, will you? You're going to use some distributive property. See what you end up with. When you're done, you can check it graphically. I think that would be the way to go. Keep in mind, X and Y should add up to 25 when all said and done. This is a mixture problem. Quite common. All right, I just did a little algebra. Did you get Y's 10? Okay. Just like I said, when I said that that's an easy equation to solve, I mean that it's not a quadratic. It's just linear. We got to do a little distributing, combining like terms. It turns into a multi-step equation, something you learned in 8th grade math, right? That means if y is 10, that would mean x is 15, right? And we knew there was going to be more of this solution, didn't we? We knew there had to be more of the 20%. Right, so that holds true. Okay, that holds true. All right. Questions? All right. What are we doing? I'm just trying to check the time here. I think what I'm going to do is cut you loose and have you get started on some work here. Now, keep in mind, tomorrow will be a little bit of a day to, if we have questions over some of these word problems, we can do that. We're not going to necessarily spend any time reviewing for the quiz, but tomorrow's kind of a day that if you did have things you wanted to go over from sections 4, 5, 6, or 7, we could do that. All right, so here's some questions to look at, some various types of mathematical modeling problems from section number 7. Okay. You'll see a couple problems like this on, some modeling problems on the quiz. Just be aware of that. But like I said, tomorrow's a little bit of day to wrap things up. We can go over some of these, and then we will be looking at a quiz on Wednesday.